Welcome back to Weather Analysis with Mr. CB. In this video, we're going to be reviewing more about the mid and lower and surface levels of the atmosphere. Um, I was hoping to do, what I was doing in an individual video for both, but I kind of fell behind with these videos later on, so I'm just going to do this all in one. So this is definitely going to be a longer lesson, I think. But it's going to be also some review of what we talked about in the last video, just to let you know. So we're going to be talking about um, the 500 millibar level, the 700 millibar level, 850 surface level. Those are the four. We're not going to talk about the upper level, but I do have a video on that if you want to know. Let's first review what station models that we have at the upper levels. Um, They have four things, if you want to say, that are around um, the initial point, and you would consider the center of that circle to be where the station is. And let's first talk about this wind direction. Where that flag points is going to be where that wind is coming from. That's something important to not mix up. It's not where it's going to, it's where it's coming from. So you try to imagine, almost imagine like that this is like a car and I'm sitting in it and that's like the seat and I'm facing like this way and I'm going like in a just zooming around. So in this case, that means the wind's coming from the north. So just imagine that's the seat and I'm sitting in it. That's the way I'm going. But so yeah, it's go coming from the north would be going to the south. Um, the TT that's on the upper left, that is temperature in degrees Celsius. When we're looking at the surface station models, we'll look at that at the end of this video. It's in degrees Fahrenheit. So that's something important to note. The DDDD is dew point depression. And if you remember what dew point depression is, that means the temperature, the degrees difference between the dew point and the actual temperature. And if that is zero, then saturation is occurring. Um, the HHH on the upper right is the height that we're at that point. Because remember, on these maps, we have constant pressure everywhere. So the pressure is the same everywhere on the map. But there's differing height. That's the opposite when it's the surface. We're assuming we're at the surface, so obviously constant height, but there will be differing pressures. So that's going to be a difference with the um, surface station model that we'll look at the end. But for these upper ones, this means the height. And they label it as HHH because it's three-digit number. But in reality, that's the decameters. We actually want meters. You put a zero on the end of that. So you see these over here. Um, 592, that's really going to be 5920 meters. Um, the PP that's on the bottom right, we really don't talk about that much, but it might be useful for you to know that it's the 12-hour height change. All right, so at the 500 millibar level, sorry about that. Um, what do we look at? First, what height is it at? Um, Around 6,000 meters, 18,000 feet. Really, in my opinion, I think meters is more useful to know because that's what's in the geocoded height. So that's how you would know that this is at the 500 millibar level because these are close to 6,000 meters if you add a zero on the end of that. That's 5920, 5930. But I should have put a thing like that because approximately, because remember, it's not going to be constant height everywhere because the atmosphere is not just the same everywhere. It just, that's the whole reason why we have these maps, pretty much. But what can you see here? The main things that you can see mid-level troughs and ridges. The mid-levels, troughs, and ridges, what is the point in that? Well, based on where they are, you might be able to even know about some things lower. Talk about that later. But the most important thing for the 500 millibar level is vorticity advection. We'll talk more about that in a second. And then you can also see some short waves. That is better at the 700 millibar level, though. We also would call this the level of non-divergence, because it so happens that often, if we have rising air in this case, we have convergence at the bottom is rising, and then at a higher level, it will diverge. But at the 500, we're not at either of those top or bottom points. So, um, it's important to note that when you have closed off height lines, there's going to be a low there. Well, not always, but we're just going to say in terms of it, you could look at the values around to know that it would be a low. And if you have a low, remember it's low height, not low pressure, because it's constant pressure. That's why it is the 500 millibar level. Um, Now we have two types of ridges and troughs that you'd want to know, which are going to tell you what's going to happen. So imagine that this is a jet streak, this little area with a circle, well, oval with the arrow. That indicates that there's faster winds there. So knowing that the faster winds are before or after the trough are going to help us know if the trough will in the future deepen or fill. If it deepens, that means it's going to get deeper or just more extreme. Filling, it's going to get more flat, kind of. Um, and that depends on if the winds are before or after. Before, it's going to deepen. After filling, it's like, okay, we're done. And it's going on. Ridges, it's going to intensify if it's before, weaken if it's after. So that kind of makes sense anyways. All right. We have vorticity that we're looking um, at 500 millibars. And what would we consider vorticity? Rotation. Okay. So that's really what we're looking at here. And there's going to be two situations where that might be the case. So we can have shear vorticity. This is kind of like a pinwheel effect, meaning if we have super fast winds in the middle, we're going to have weaker winds as we go out, because you will have situations where if there's a channel of stronger winds, it will get weaker as you go on the outside and stronger in the middle. And the um, parcels that we have are going to, you would imagine that they'd spin like that, almost like gears grinding. And so above the fastest winds, it's going to have cyclonic flow. Cyclonic flow is counterclockwise flow. Anticyclonic flow is if it's below the fastest winds, and that's clockwise flow. Curvature vorticity is flow around the curves of ridges and troughs, and that results in a spinning um, particle as well. Um, Now, if we're talking about vorticity advection, what would that mean? Well, you have to try to think about what it means for something to be advected. Um, so in this case, when we're talking about it, we're saying, if we have positive or negative vorticity advection, um, we're having uh, a particle being advected, and based on where these situations are, um, you will be able to tell some more things, and I'm gonna get to that later. Um, so I kind of wanted to explain that better. So for advection, that's basically horizontal movement across, in this case, it's typically west to east. We know that's the way that these winds are flowing. So for the vorticity advection, we're having that vorticity moving across is essentially what we're talking about. But Um, if we have positive vorticity advection, higher vorticity is about to go there. I don't know why it says above to go there. About to go there. So in this situation, we have positive vorticity advection right here because this is about to be advected here. Um, this is a map of advect or vorticity, and there's higher vorticity in these dark colors. They're about to go there because you can see this is like a path that it's going to take. So if higher vorticity is about to go there, there's positive vorticity advection. Now, on the other hand, this we know that these dark colors were here, so where they used to be is where negative vorticity advection is going to be. And around here, it's pretty much static across. So that would be considered neutral vorticity advection. So what will a particle do as it goes through a trough? We have to know that because of the fact that we have curvature vorticity, as I mentioned, it's going to spin, but the basically two things are going to happen. As you can see, this horrible drawing. Apologies for that, but um, it's going to start out like that. But once it gets to there, it's going to be stretched vertically and compressed horizontally. You can kind of imagine um, if if I'm like ice skating, which I never have, but if I am, if I have my arms out like wide, I can't go as fast. Um, because I'm essentially having creating some air resistance. I guess that's what that'd be. And then if I go like this, which would mean I compress horizontally, then I can go faster. So you can think about it like that, but you also are stretched, it's stretched vertically like that. And then once it leaves, it goes back to normal. Short waves. Short waves, first, let's talk about what they look like. You can see them by looking like a slight kink or deviation in the flow, meaning the flow just randomly has like a little divot in it. And you can see this is a kind of bad drawing, but that's kind of what it would look like. It's not, I mean, it goes down a little bit. It's just a slight divot in it. I guess if you thought about this like a road, it would look like a pothole or something. Um, we're going to talk more about what they are with this level, the second level in this video that we're going to talk about, because you can see them at the 500 millbar level, but going down lower, because of course, as we go lower, that's a higher pressure. But the short waves are more easily identified here. The height of this level is approximately 3,000 feet. So the level or the HHHs that you'd see would be around, they would be something in the 300s because that's decameters and you add a zero for it to be normal meters. Here you can see uh, upward vertical velocities, omega values associated with that. We'll talk about that. Short waves, as I mentioned, and inversions. In general, I also wanted to mention that if we're talking about zonal flow, that's going to be west to east flow. Meridional flow, north to south. Um, just wanted to mention that. Short waves. So, as I mentioned, same thing for this level. It's going to look like a little pothole if that's a road. Um, and we are going to have cyclonic flow when that happens because you know that it's going this way, so it's going to go and curve like that. That would be counterclockwise, which is cyclonic flow. Um, Here, what we can know is that there's slightly colder air here. Um, and that's going to be important for when we're talking about thermal advection that we're going to talk about a little bit later. Um, so here's a little test to see um, where would the low pressure be on this map. This is a 700 millibar map. It's going to be to the right of the trough axis. So this is actually not the best example. I pulled this from the current time when I did this, which was earlier today. So there's not a very evident trough, but this is where we would consider the trough axis, and that's positively tilted. If that's like a slope, like that's a positive slope. So it's positively tilted trough axis. And so the low, it's not going to be right on that trough. It's going to be to the right of it. And the thing is, the lower you get in the atmosphere, the closer that L is going to be to the trough axis. Once we're at the surface, the L is basically right there. Because that's the way, if you remember, skew T log P, all this stuff's starting to connect. There are relationships between pressure and temperature. They're not just abstractly related. They um, are related, well, if you can think about it by the gas laws, that you may have learned before. I'm not going to get into that, but that's the reason why this works out like this, depending on what level you are in the atmosphere. But basically, in short terms, just know that the low is going to get closer to the trough axis as you get lower in the atmosphere. Um, okay, so where would a front be? You might be able to detect a front at the 700 millibar level by multiple kinks all the way down. Okay, maybe there's cold front right there. All right, omega values. Um, Omega values are basically able to tell us if we have rising or sinking air. If we have a positive omega value, sinking air is going to uh, be what there is. Negative omega, rising air. And we can think about what would happen above and below for both of this. So above a positive omega value, above where there's sinking air, there's going to be negative vorticity advection, and below cold air advection. That's what CAA means, and that's at the 850 level that we'll talk about in a second. But that would make sense. Sinking air, uh, if particle is cooler than its surroundings, it will sink. Um, Rising air, uh, above positive vorticity advection, below cold air advection. It's important to note that if the relative humidity is 90% anywhere around here, then the chance of precipitation is close to 100%. Right. So one more thing that I wanted to say for the omega values, they're used for identifying the upward vertical velocities. And you can see some maps where the velocity in millibar per second is shown. And that's how we would get these omega values. All right, we can also have some convective forecasting at this level. So there can be an inversion here. And if so, convection is inhibited because there's a stable layer sooner than normal. So if you think about it, the tops of our thunderstorms are usually way higher, almost at the 300 millibar level, because it takes that long for us to get to a stable layer. And if where there's a stable layer, we would identify that there might be an inversion by the time we get to that. But if there's inversion at the 700 millibar level, then that's what can help us with convective forecasting. And there's two types of inversions that we could have. This a subsidence inversion, which is caused by warming from above. That's going to cause downward motion, or radiation inversion caused by cooling from below, which is upward motion. All right. It's also important to know for the dew point depression at the 700 millibar level, if it is 5 degrees Celsius or less, there may be heavy rain as a lifting mechanism. That's something else that you can know at this level. All right, now, sorry, I was uh, looking at an email that I got. At the 850 millibar level, that's going to be at about 1500 meters. which we would identify as decameters that are close to 150. Um, at this level, we can see some thermal advection, which would be warm air advection or cold air advection. We can see frontal boundaries relatively easily here. Uh, it's essentially a surface map for the mountainous areas because the mountains are so high that they're already almost at this level, so it pretty much is the surface. Um, and we can also look at a low level jet. Fronts at this level um, are going to be to the right of the low in most cases. And to know where a front might be, you can look at changes in temperature, moisture, and wind direction. So here you can see these winds. You can see right here they're coming from the north, but then they're switching, and then right here they're coming from the east. So there might be something somewhere around here. That's something that you can look at. And then here there's a major difference in moisture too. So these are some of the things you can look at. Flow at this level. Now we're starting to get closer to the surface, so no longer will we be in geostrophic flow. If you remember back on that older lesson, geostrophic flow is going to be if we're going parallel to the height lines. Well, now we have some friction, so it's going to be uh, tilted and ageostrophic, so it's going to slightly go over the height lines. And if you want to remember why, please watch that other video. It's about like the forces changing and they're no longer balanced. But regardless, we're not going to get the parcel is not going to flow directly parallel to the height lines anymore. Um, Thermal advection. So basically, this is going to happen where the wind, where it's flowing, is going to intersect with the height lines. Um, this means that the wind is actually moving up and down in height instead of just at the same height. It's not going to necessarily be perpendicular. So you can see this example, the way this wind's flowing is not perpendicular exactly. It's just at an interesting angle that's in between, you know, 0 and 90. Where we have cold air advection, we're going to have downward motion and compression of the atmosphere. Warm air advection, we're going to have an upward motion and expansion of the atmosphere. Low level jet at 850 millibars. So the low level jet, just like any other jet that we've talked about, is going to be higher wind speeds. It's going to be in the warm sector of the mid-latitude cyclone. And this is what a mid-latitude cyclone looks like again, by the way. Uh, we have the warm front on top and then cold front like this, and the low is going to be close to where they intersect. Um, and the low-level jet is going to be in this area, which is considered the warm sector. There are three associations I just mentioned that it can be in the warm sector. Um, we can also know where we would have the exit region of the upper level jet. Below that will be the lower level jet. Also, we can have a low level jet due to nocturnal cooling of the Rocky Mountains. Um, Basically, we end up having lower pressure on the eastern side of the Rockies due to air um, sinking. And we know that the pressure gradient force is going to go from high to low pressure, so it's going to go from east to west. So that can be a third reason that you'd have it. Now, the surface station models. So we talked about in the beginning of this video the upper level. The lower level, this might be what you're more used to anyways, but there's a little bit more things with this one. We'll start over here. So on the top left, it's temperature, this time in degrees Fahrenheit. Um, right here is going to be the dew point. So no longer is it dew point depression, it is actually dew point. The dew point depression in this case would be 1 degree. Um, the symbol that's in between those is weather, what weather we have, and And when it circles like that, you don't really have to know this, but you might want to know this. But in this video or this portion, you don't have to know this, but uh, the circle is going to be rain, and the more dots, the heavier it is. And you could also have asterisks for snow. You could have that symbol for thunder and other things too. But the station center is going to tell us sky cover, which is we consider in octas, which means that there's basically eight different possibilities that you could have for this. But basically, the more blackened out that is, the more clouds we have. If it's completely black, it's overcast. In this case, if it's like that, it's clear when it's just open. We know about the wind barbs already, but um, we know that this is basically northwest winds coming from the northwest, but the actual barbs, I haven't really talked about the values of them. But if you have a triangle that's 50 knots, we measure in knots. A full barb that's like goes out as much as the triangle is 10 knots. If it's only half, then it's 5 knots. Um, and sometimes we'll see a G with a number by that too, which would indicate gust that we would have. Top right is going to be pressure, and it just like how when it was height with the upper level plots or upper level station models, it's coded same thing for this. And this one's a little bit more complicated. You don't put a zero on the end of it for this one. For this one, you actually add at the beginning a 9 or a 10. And how you know is basically whatever is closest to 1013. If you put another thing that I should have said is there's always a decimal here. So you're going to put a number here and whatever's closest to 1013 because that's just basically neutral, not high or low pressure. Is going to be what makes sense. So you could put a 9 or 10 here. So if we put a 9, that would be 910.7 millibars. That's not going to be what it is, even though that is possible. That's probably not expected unless we had a tropical cyclone and seeing these temperatures and wind, that's not really what it would be. And especially since it's clear. So that's not really what it would be. Instead, you'd put a 10 there, so it's 1010.7. That's more like it. That's is what it would be. And you might have a different situation like if you saw 838 or something, then you would put a 9 there because 983 makes more sense than 1083. 1083 is a really high pressure that we wouldn't expect. Um, this bottom right is the pressure trend, basically saying how we think the pressure is changing with height. Um, and there you go. That's what that is. So now we're going to talk about the last thing in this video is just a little bit of data that we can use. We have METAR, which stands for Meteorological Terminal Air Report. Basically, we're using code um, to identify the conditions that we have, is what this is. And it's very commonly used in aviation, and this is something it'd look like, but all of these different items indicate different pieces of information. So, um, for example, this one, FEW, few, I don't know why I spelled it out, but we're going to identify as that being the octa that is few clouds. Um, but you don't actually really have to know what this means for this course, but you just want to know what it is. So then there's ASOS and AWOS, which this data can also be used for aviation, but we're going to have instruments like these to give us this data. So AWOS and ASOS are based off of similar data, but ASOS is newer. We used to have just AWOS, which is Automated Weather Observing System. We have more stations for this at this time since it's older. and it can report in 20-minute intervals. ASOS is Automated Surface Observing System. It's the newer version. It reports hourly. Once again, this can be useful for aircraft. So that's all for this video. Thank you for watching.